As Lorenzo stressed, this is really a space in which we're going to construct a solution. So it's something which depends on what you have, the structure which you had before. So it depends on the abstract. So it depends on the regularity structure on the abstract side. So the set of homogeneities, the model space, and the structure group. And it depends on the model itself, which was given by the evaluation map and the change of base point transformation. And it's you call an application from space or base point into the abstract model space. You call this a model distribution of order gamma, provided there are two properties. So the first property is just that for every x, f is in the space of homogeneities less than gamma. And the second property is this crucial continuity property, which we've seen as kind of a generalization of Hölder spaces. So if you compare the model distribution at two different base points and you use the change of variables to compare them, and you look at the component alpha, so in T alpha of the result, then this abstract vector should be small if x is close to y, and it should be small in a graded way, in the sense that it depends on the distance. So in my case, I'm using here the elliptic distance, but you could also use the parabolic distance, like Lorenzo introduced it, to the power gamma minus alpha, which is a positive number. And this constant, the best constant here, you may consider as being the norm, this generalized Hölder norm of f, or the Hölder semi-norm, to be more precise. And this is supposed to hold for all x minus y less than 1 and all alpha less than gamma. There's nothing for alpha larger or equal than gamma anyway. So so that was the definition of a model distribution, and I gave already two examples which showed that this was really a generalization of Hölder spaces. But then I announced a third example, which was related to my toy model. And let me recall the toy model here. So we were interested in the solution, and this time I'm going to put a small massive term because that simplifies some of the it simplifies the discussion. It's not necessary otherwise. It makes it in a certain sense a little bit clearer what I mean by the objects. So we're interested in the solution to this equation, where this here was something which was smooth and compactly supported, and this was white noise, and the dimension was 5, so that we had the same numerology as in 543. And we saw that by completely kind of PDE type of analysis, we were led to, in order to describe this object, we were led to introduce a couple of auxiliary functions. And if we wanted to go one step further, which I did at least on the slides, there would also be this function around. And by standard Schauder theory, since psi is in almost minus 5/2, we get that V is still a distribution. The VI's are already functions which are Hölder continues, and the next step would be something which is already differentiable. And but then it turned out that so why did we introduce these things? We introduced these things because it was absolutely easy to see that this kind of locality principle, which showed that, that if we were subtracting from this distribution, which is just of order minus 1/2, this object, which is a distribution of order minus 1/2, we actually got a function of order 1/2. And if we were subtracting more, minus di eta vi, we were getting to 3/2. And if we are subtracting even more, and I want to write it in the way we did by kind of subtracting the value at a given base point, because that's convenient. Plus 1/2 dij eta vij minus the Taylor polynomial, first order Taylor polynomial, so vij x minus x dot gradient vij x. And this was already in C5 halves. And the interpretation was that these functions can also be looked upon in a different way. They in fact are solutions of, so now I have the massive term, of, so if I take v and I multiply it with a coordinate function anchored in x, and I add to it vi, then this was nothing else than solving the equation with the right-hand side, where I multiply the white noise with this first order function, and the same is true to next order and of course to any further order. Okay, so that's just recollection of the of this toy example. And I stress again, the toy example was not, of course, not at all interesting by itself. It's just a good way to illustrate both what I already wrote down last time, kind of the separation between algebra and analysis, and it helps to digest regularity structures. So now I want to put the kind of the solution of this problem, as we understood it in the first lecture, as being, you know, something local plus something non-local, in this language of model distributions, very much like in the real application to 543, you write the solution as a model distribution, and you gain the solution as a model distribution. And so I'm going to do that on the first level, not on the second level. I will put the second level on the slides, and I do it here on the first level because otherwise I would just write too much. So first level. So the statement is that the following object is kind of the right way to dissect the solution. So there is the completely algebraic part, which multiplies the placeholder for the noise and the placeholder for this object. So that's what I called kind of the algebraic.
Don't you want to put I in front? I noise and I excite?
I?
And they're integrated objects, no?
Yes. Yeah, thank you. Good point. Yes, that's what I mean. So that's the algebraic part, or the local part. And then the analytic part, or the PDE part, is in what comes next. And I already wrote it down last time. I write it slightly differently, which makes it even more transparent. So this is phi minus eta v evaluated at x times 1 plus di phi minus eta v minus dj eta vj minus vj of x evaluated at x times xi. And that's the analytic side. So, and so let's first check that what I write down makes sense. So while phi certainly is not a function, so I could not write this down as a coefficient, we've seen at the very beginning that this combination indeed is a function. So I can write this down. And we've seen in the beginning that this combination even is a differentiable function. So I can write down its derivative and evaluate at x. So what I wrote down makes sense. And for me, this is really, in a certain sense, this was helpful to see because it really pins down this point that there is kind of this algebraic aspect to regularity structures, where you see kind of a completely local behavior. The singularity shines through in a completely local way, which is sitting in this first part. But as Lorenzo said yesterday, you shouldn't be carried away. It's not, I mean, you didn't algebraize analysis. Analysis is still there in its full right, but it's sitting in the polynomial part. That's where the analysis happens, and that's where kind of PDE theory plays a role. So now the claim is that this is a distribution, a model distribution of the order it should be. So we're essentially integrating up a model distribution, which in example 1, if we truncate it, have seen to be of order minus 1/2, and we're integrating it up. So what we get should be of the order 3/2. So we should see that this model distribution, and again, this is, I think, a good exercise, which I want to do here. We should see that this distribution satisfies this continuity condition. So that means, oops, morning exercise, we have to look at this expression. So we're looking at two different base points. We consider the appropriate change of variables. So now I'm plugging in the formula. I'm using the linearity of this object. So I get the following expressions. I xi minus eta of y, gamma xy, I xi. That's from the first term. And now I use what we've seen last time, that the change of variables on this object here, because this is still corresponds still to distribution, is trivial. So we get this for the first term. So then let's look at the next term. So we get di eta x I xi xi as a placeholder minus di eta y gamma xy I xi xi. And this is since this corresponds to distribution which is of positive order, because minus 5/2 plus 1 plus 2 is equal to 1/2, there is a non-trivial action of this gamma, and we've seen that this is given by, you always get this back, and then there is an easy polynomial part, and then there was the only interesting part, which was Vx minus Vyi times 1. Okay, so that's what's happening on this term. Then we have the one term, so plus phi minus eta Vx1 minus phi minus eta Vy gamma xy1, which of course is 1. Nothing happening there. And then we have the last term, which is phi minus eta v di phi minus eta vj minus vj x x xi minus the same thing at y. At y, and then applied to gamma xy times this here, which is capital the placeholder I plus x minus y times 1. Okay, so that was just mechanics, and now of course we should arrange them into the components, and there are the following components. Well, let's leave a little bit of space. Let's start with this one. This one comes up here, here, and here. And so I have to put up eta x minus eta y minus x minus yi di eta y. Now that's a good term, because by smoothness of eta, I know that this is of the order of x minus y squared. The homogeneity of this guy is minus 5 over 2 plus 2, so minus 1/2. And indeed, that's the exponent which I would expect, because 2 is equal to 3/2 minus 1/2. So that component satisfies the continuity condition. So now the next term is, let's take I xi xi. That's easier because that only comes up here. So this is di eta x minus di eta y. This is first order. This here has homogeneity 1/2. And again, 1 is equal to 3/2 minus 1/2. So that has the right behavior. Then we have all the stuff which gets into 1. So that's where most terms come up. So we have this, phi minus eta v at x minus phi minus eta v at y. But then we also have this term here. So this is minus di eta y vi x minus vi y. Then we have the term which is sitting here. This is also minus x minus yi di phi minus eta v minus dj eta vj minus vj of x at point y. And now you should see that if I give this function here momentarily a name, wx, so that's a function which depends on the base point x. It's a function of the active variable z. That this thing here is essentially the first order Taylor polynomial of this function, so vxx minus vxy minus x minus yi di wxy. But then there is a little error which is of the form, let me look it up. Which is of the form minus di j eta of y v j of x minus vj of y times x minus yi. So if I did do the algebra correct, this is how you can organize this term. And now you remember from PDE theory that this is 3/2. So that means this entire term, because it's the first order Taylor polynomial, is of the order x minus y to the power 3/2. And so is this term, because Vj by Schauder theory is C1/2. So this is of the order x minus y to the power 1/2. This is of the order x minus y to the power 1. So also this term has this behavior. And that's exactly what we need. No more and no less, because the homogeneity of 1 is equal to 0. So we want the exponent 3/2 sitting here. So it all fits exactly. And then there is the last term, which multiplies the xi, and that turns out to be di wx x minus di wxy plus or minus this term. And again, this here is, as it should be, of the order x minus y to the power 1/2. And this, the homogeneity is equal to 1. And 1/2 is indeed equal to 3/2 minus 1. Okay, so that is just to make the point that this continuity condition is a miraculous condition. It encodes in a very efficient way all the kind of different levels of continuity which you want to encode. And in case of our toy example, it's just kind of standard PDE theory, so Schauder theory, which we applied here, of course, several times, which just gives us the desired information, namely that the solution of this problem, which we organize as a model distribution, is indeed of the desired order. Yeah, so I think, I hope that this gives you a little bit of a feeling of the texture and the flavor of the problem. I think it's important to see, besides commuting diagrams, to also see a little bit what texture the problem has, and that's really kind of the analytical texture of this problem. Okay, so are there any questions? Yeah.
Where did the second part of the contribution to the xi come from?
This part here, or which part?
Exactly this one, yeah.
This part. Well, we should. So let's look at where it comes from here. This term here is exactly that term, because if I evaluate the function wx at x, this term drops out. So there is one-to-one correspondence between these two terms. Now you want to see this term, and you almost have it. So let's see where. So is that? is that equal to this? So I'm substituting now y, so I get wi of y, and I get an eta I of y, so that looks correct. And now here, I have delta eta at y, but I want delta eta at x, because I want the x here so that I can compare these three functions. And therefore I have to, in this thing, I have to go from y to x, but this thing only matters if the derivative hits this factor, because if it hits, y, x, right, okay, let me not, I'm going to get messed up, but it has to do with the fact that here we have a y and we want an x. And we have to correct this, and that gives this term. Okay, thanks. Okay, so that's the argument. Are there other questions? Yeah.
So here is, so the point that here phi minus eta minus the IV minus this in C3 for any choice of x, whatever the
Yes. Well, I mean, that's no big deal, because eta is smooth, and changing the x just does something, adds this term. So that this is true for any choice of x is not a big deal. It's just convenient to write the term like this. There are different ways why one thinks, or why it's good to write it this way, because so if you didn't have the massive term, vi would not be stationary, only increments would be stationary, so therefore it's natural to put it there. But also kind of the notion of regularity structures always needs a certain degree of vanishing in the base point, and therefore, but we'll see that in a second much more clearly, we want such expressions to kind of vanish if you approach the base point. And but here the fact that, I mean, this statement is likewise, this statement, I'm just also the fact that this holds for every x is not the main point. The main point is that indeed you end up, despite the fact that all the three ingredients are worse objects, that this particular combination is of better order, and that was just a consequence of Leibniz rule and the definition. Okay, so right. So now, then yesterday I mentioned reconstruction. We'll go back to that. So also I want to give you kind of very efficient proof of the reconstruction statement, but rather tomorrow. And now, because Lorenzo needs it, I want to say more on integration on the abstract level. So on the general level. Here in a certain sense, here with example 3, you have already seen integration on the level of this toy example, how kind of it gives you the solution as a model distribution in the right continuity class. But now I want to introduce kind of the terminology in the general case for the integration. So that would be, if 3 was reconstruction, 4 is integration. And as always with Martin's setup, it comes in 3 layers. There is something on the layer of the regularity structure. So on the level of this triplet, and that object will be the I, which as a symbol we already introduced in a suggestive way. Then there will be something on the level of the model, So that was the level where pi and gamma lives. And that will be something which is called J. And now that's unfortunate because in Lorenzo's slides, his eye looks like this J. I think I'm closer to the master. So if I look at Martin's script, the I looks like this and the J looks like this. And
yeah, but that's his fault because he uses LaTeX packages that I don't control. So
okay. So and then there is the level of a model distribution. And there is a third object which Martin calls script M. So now I want to introduce these three objects, and I want to discuss them again on the level of the toy example, because then I hope it will get somewhat transparent. So let's start with this level. So before doing so, I will now assume that the polynomials up to some sufficiently high power are always included in the regularity structure. So that means they're included in the set of homogeneities, in the abstract vector space, in the structure group, in this trivial kind of where things are pretty trivial, but they're also included on the level of the model and the transformation in the usual way. So it's kind of a I think Martin calls it a sector. So will not define that because I think it's intuitive what's meant, and we used it already in the example. So what's this object I? So the postulate is that I is a linear map on the abstract vector space, which has the following properties. Three properties. So it should increase the homogeneity by 2. It should vanish on the polynomials. So this should be included in the kernel of I. And the most subtle condition, the only one which is not tautological for our example, is that if you look at the commutator between an element of the structure group and I, then you want the image of this commutator to be contained in the kernel. Be contained in the polynomial space. So these, in other words, the operators commute up to polynomials. So those are the three abstract conditions, and let's immediately make a sanity reality check that this fits nicely with our model. So remember that in our toy model, toy example, we had the following three groups. So we had the noise, and the noise times polynomials. We had the polynomials, and we had the solution operator applied to these objects. Okay, and so clearly, so now if we take this this stance, which is suggested by the notation, that we now give a life to what before was just a ladder, namely that we think of these here as being the images of these basis functions defining a linear map, then certainly this is trivial by definition of the homogeneities. This is trivially satisfied. This is kind of satisfied because I didn't write down, I didn't include I of 1, I of xi, I of xi, xj into the model. And so it's a little bit fishy because, of course, this would require, I should also apply I to these objects, but let's say up to the fact that I'm ignoring I square. And now what about this? What about this this commutating relationship? So we have to check it. We have to check it on, for instance, the noise itself. And it's easier to check it in this form using nilpotence. I gamma minus identity times theta. And in this case, the answer will be 0 because both of these objects have negative homogeneity. That means the change of variable acted trivially on them. There was nothing to kind of subtract. So this is equal to 0, and this is equal to 0. So this is equal to 0, and therefore, in particular, a polynomial. So now, on the next level, we have to look at this. So here the structure group the structure group acts like on a polynomial. So this was given by something, some number AI times the noise. And on this side, there was something interesting happening. So there was this trivial part, which in a certain sense was representing the polynomial structure. So AI I gamma xi. But then there was this interesting term that there was a spillover into the 1, vi times 1. And now these two elements cancel, and what we're left with is just bi times 1, but that's okay because that's a polynomial. And now if you do the same thing for xi, xj, and I'm not going to do this, you get the answer that this is equal to some constants g is c ijk xk plus dij1, which is again okay. And here I'm using the same letters which I used on my slides when I wrote down this big matrix representation of the structure group. So so that's this property, this commutator property is satisfied in the case of our example, and so therefore it looks reasonable to impose that. So we've done this. Now this is more, this was kind of completely algebraic, if you want. Now the next step is analytic. Oops. so now we go on the level of the model. And there we impose that there exists J, which now is a field. So this is something which to every base point attaches a linear map on the abstract vector space. So if you want to every base point, it attaches a linear transformation Jx tau in T with the properties with the following two properties. The first property is that the image is always a polynomial. And the second property is, and that's the first property that makes a relation between kind of this abstract level and a PDE. And now let me take not the parabolic but the Laplace operator, as I've done in my example, and let me also do it with a massive term, as I've done over there. So you want the following. If you take I and you look at I tau, so this now is an element of T. You correct it by Jx of tau, and so this is still an element of T. Now you bring it into the real world by applying pi of x. So this is now a distribution. Now you want this to be pi of x of tau. So in a certain sense, you want indeed this symbol to be essentially what's happening on the abstract side if you solve your equation. But it's not quite what's happening. You need a correction, and you will see it on the level of the model what this correction is. And the correction is this j of x. So that's the second condition. And in case of our toy model, this object is an old friend. So j of x applied to xi is 0. So there's no correction. J of x applied to xi times xi is vi of x times 1. So again, even if you didn't like the introduction of these functions, they would come back at us now because they appear in this structure. And j of x xi xj xi is equal to something which involves both functions, is equal to vij x1, and then there is oops. And then there is a linear part to it, which consists of two terms, vi of x xj plus vj of x xi plus gradient vi j of x capital X, which is all the xi's put together. Okay, so
The j of x, are those the counter terms?
those are no. I mean, I wouldn't. So far, this has not to do with the renormalization, right? I mean, in the end, it's of course related to renormalization because the entire thing is related to renormalization. But these terms already come up in this toy model, where there's nothing to renormalize. It's let's see why. Let me explain why, in case of the toy model, this term comes up. Yeah. And then perhaps it becomes clear of what flavor they are. So, so let's check this one. So first of all, sorry, I did something wrong. I wasn't precise enough here. So this should be a polynomial of the order x. So if tau is in T alpha, this should go to up to alpha plus 2. That's important. Sorry, please correct that. So so we have both conditions to check. This condition is satisfied because if I look at the homogeneity of this symbol and I add 2, this was minus 3/2 plus 2 is 1/2, and the largest integer below is 0, and therefore this just contains the 1. Whereas if I would do the same calculation on this level, I would gain 1 here, so this would be 1, so this means it's okay to add the linear term. So so that condition is satisfied for the middle term. Now what about the equation? So I just first copy this. Okay, so now I have to remember what the how the model was defined. So this I did yesterday or the day before. So this here, and I want to do this now for this specific tau. So xi minus pi x j of x xi. So how was this defined? That consisted of the term v minus plus vi, and now comes the culprit, minus the I of x. Remember that we had to subtract this in order for the model to have vanishing of order 1/2. And now this term does nothing else than removing this term which we put in there. So these two terms cancel, and therefore, where is it? No, on the other blackboard. Therefore, this equation kicks in, and we get that this is equal to minus I xi, which is, again, by definition of the model, pi x applied to xi times capital Xi. So in a certain sense, these j's have to do with the fact that the notion of a model can kind of impose this vanishing order. Yeah. Sure.
The way you define it here, the j is only well defined because you have the mass, right? Because otherwise, whatever polynomial you put, it would always be true.
As long as it's a harmonic polynomial, correct? Yeah. So in fact, Martin does that with kernels.
Yeah.
In which case, it's clearly invertible. And now, for the purpose of this discussion, it's clearer to put in the mass, because then you see that this here. So I don't like, I like to write down a PDE. I don't like kernels so much, and so therefore, okay, so I have to put in the mass so that this is kind of this defines the J. That's
Felix, I think you forgot writing an xi in front of xi.
I forgot what?
With pi x j of x xi xi.
Here in this, which line? This line? I forgot.
Also to the right. No,
Oh, to the right.
to the right.
Upstairs.
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 xi.
Yes.
Capital X.
Thank you. Okay. So that's the role of the J's, and there is one nice. So in a certain sense, in a certain sense, you see that the J's are a little bit, they're imposed on us by insisting on that the model vanishes to the order of its homogeneity. The price to pay for that is the introduction of the J, and in fact, the right quantity is really I plus J. That's the natural quantity, and that comes by the fact that there is a general formula or consequence, or let's say corollary of definition. If you look at I plus J, if you don't pull them apart, then it nicely intertwines with the change of variables. And that's, so I don't think I have time to give you the little argument for this, but it's a nice exercise to show that it follows from just the abstract definitions and uniqueness of the solution of this PDE with a massive term, that you get this formula. And that tells you in a certain sense the natural object is really I plus J, because that's the object which has this intertwining property with a change of variables. Okay, so this is a bit of a nuisance, but that's how it is. And that settles this part. And what's the question?
So I is Laplacian inverse or Laplacian plus m square inverse?
Depends on which equation I want to look at. But here you should think of it as being the symbol for the inverse of the massive term with the massive term.
Then could you remember why all these polynons are in the kernel? Is kernel. So the second.
Oh, that's something which you impose. I mean, the I is not so. The I is not the I is not really the solution operator, right? I lives on the abstract level, and it has to do with the solution operator in the sense that it gives you the leading order part, but anyway, you have to correct it by the J. So you should not think of I as being really the solution operator, because you insist on, for instance, that it vanishes on polynomials. And of course, the true solution operator, it vanishes on placeholders for polynomials. But the true solution operator, of course, would not, when you have the massive term, would not vanish on polynomials, not even on polynomials of first degree. So it's, I think it's important to keep that apart. So I is not, I is kind of the algebraic part of the solution operator. And it precisely does not see the analytic flesh, which is sitting in the solution operator. Right? I mean, it's really, on the level, look at this toy model. I mean, I is nothing than, kind of, it maps this basis function onto this basis function, it maps this basis function onto that one, and this onto this one. I is just a finite dimensional linear map. Right? And its connection to the solution operator is only happening in this line. Only this line connects I to the PDE at hand. It's only this line which connects I to the PDE at hand, and it does so in a convoluted way. I mean, first you have to kind of go from the abstract space to a concrete distribution by applying your model, and then you have to correct it, and then it satisfies the right equation, again with the right-hand side, which is given by the abstract object, made into something concrete thanks to the model. So I mean, you know, I could write down a commuting diagram. So down here is what the solution operator does, what the PDE does, and in a certain sense, part of it is described up here by the I. But in a certain sense, the analytically trivial part is described there. Does that make somewhat sense? So I think it's really helpful to think about this, about the toy model, right? Because there everything is specific and explicit. The I is just it's just a linear map. Okay, can I still write down? Yeah,
Quickly.
So because I promised to
And without toy model, how it is exactly defined, this J? It's only this condition. Which condition?
So on the abstract level, the J is defined by these two conditions. It's
In
determined.
the second condition, you have m squared minus.
Right. I mean, now replace that by your whatever differential operator you want to consider. So that's not related to the toy model. And in the toy model, we convinced ourselves that it's given by these formulas. So that's the abstract principle, where here is sitting your differential operator of choice. And in case of the toy model, you convince yourself by the argument which I've given here that J can be expressed in terms of the functions which we anyway have. Do I quickly? Okay, so I just wanted to, because I promised to perhaps Lorenzo, you can borrow me 2 minutes to write down the, or I mean, I can also stop here, so you tell me. So I wanted to do this model, explain what integration means on the level of the model distribution. If you do it, or it's okay if I do it tomorrow, then I stop here.
Go ahead.
So that means he gives me a bit of his time. Okay, so. So the last level, what does it mean on the level of the model distribution? So on the level of the model distribution, so you give yourself a model distribution f and some base point x, and we define now something which is called n f of x, and again by two conditions. So the first condition is again kind of a polynomial condition. N of x should be in the span of the polynomials up to degree gamma plus 2. And the second condition is kind of the real condition, the condition which connects to reality. And that condition being that if you look at the following object, I f of x plus j of x f of x plus n f of x, and you transform it into a distribution, then this should solve this here up to local error in the weak norm of gamma. And this implies that the reconstruction of, let me call this script k of f of x, the reconstruction of k of f is the solution of with the right-hand side, which is given by the reconstruction of f. That's almost tautological, and the theorem, and that's the second theorem which is integration, tells us that this object, which you defined here, so the kf, is a model distribution of 2 degrees better. And this, for this one, we need gamma larger than 0 to be able to speak of the reconstruction. So, so that's, I will stop here, and I will explain that better next time. That's how on the level of model distributions, you use I, you use J, you use this part here, which again is where the analysis sits, to define an integrated model distribution which has the property that its reconstruction satisfies the equation with the reconstructed right-hand side, and it's indeed of this better class. So the continuity estimate sits here, and we've checked it in case of the toy model. This example 3, which I did, was just checking this statement on the level of the toy model. And now this holds in general, provided you define it like this. And I'll explain that better next time. So the plan for my last hour tomorrow will be to give you a short proof of the reconstruction theorem, which I stated yesterday, and then if I can, give you a proof of the integration theorem and make it a little bit more transparent. So sorry for being over time.